Hello, my name is Jialin Li from the National University of Singapore. In this presentation, I will talk about our work Pegasus, a new approach to load balancing in distributed storage systems using an in-network coherence directory. So this is collaborative work with Jacob Nelson, Ellis Michael, Xin, and Dan Ports. Real-world workloads are often highly skewed. For example, a tweet from a celebrity like Justin Bieber can attract millions of views, retweets, and comments. But if you look at tweets from other non-popular people like me, well, they basically get zero traffic. In fact, the workloads commonly follow a power law, where a small percentage of popular items accounts for the majority of the traffic in a system. At the same time, the set of popular objects are not static. They change dynamically and rapidly as new trends rise and fall. These skewed workloads present a major challenge to distributed storage systems. As objects are partitioned in a distributed storage system, the server that unfortunately stores some popular objects will receive a lot more traffic than the others. If the objects becomes popular enough, it may even overload the entire server. To avoid servers being overloaded, operators need to significantly over-provision the system, wasting resources and incurring higher cost. Real-world workloads are not only highly skewed, they are also quite diverse. For example, if you look at Trader's paper, which was also published at this conference, they report that their storage systems are dealing with not just read-heavy workloads, but also read-write mixed and even write-heavy workloads. The variance in object sizes in these systems is also quite big. The implication is that load balancing techniques that target one specific workload, like read-heavy with tiny objects, will not work well in a real deployment. So what are the existing solutions that deal with these highly skewed workloads? Well, there are two common approaches. The first approach is to cache the most popular objects in a faster caching tier. The caching tier then can absorb traffic going to these popular objects, and as a result, making the load on the backend storage servers more uniform. The second approach is to replicate the most popular objects on multiple servers. Requests to these objects then can be forwarded to any server with a copy, effectively distributing load across the servers. Unfortunately, both of these approaches have significant limitations. A caching approach is only effective for read-heavy workloads, because write requests still need to be processed by the backend storage systems, and they will incur extra cache invalidation traffic. Caching is also only effective when the caching tier is magnitude faster than the storage tier. As storage systems themselves are getting faster, for example with in-memory storage and new non-volatile memory technologies, an in-memory caching tier is no longer effective for load balancing. Recently, there are proposals to cache data directly in the network switches, but that approach also comes with severe limitations, like restrictions on the size of the object. While in a selective replication approach, as the workload is dynamic, it is very challenging for the clients to track which set of objects are currently replicated and the location of the copies. Existing solutions also either do not provide strong consistency for the replicated objects or use very expensive coherence protocols. So is there a way to overcome all these limitations? Well, the answer is yes. Now let me introduce to you our system Pegasus. Pegasus is a rack scale system which consists of 32 to 128 storage servers connected to a single programmable top-of-rack switch. Pegasus overcomes the limitations of existing solutions. Specifically, it provides good load balancing properties for highly skewed and dynamic workloads. It works with fast in-memory storage systems. It is effective for any object sizes and workloads with different read-write ratios. And lastly, it guarantees linearizability. Our key observation is that in a rack-scale system, even when some of the servers are overloaded because of skewed workload, there are still spare processing capacity elsewhere in the rack. So if we can replicate popular objects to these servers and steer traffic to the appropriate servers, we can effectively balance load in the rack. But there are two challenges. First, how do we route client requests to the right servers? And second, how do we guarantee consistency among the replicated copies of these objects? In Pegasus, we address these challenges by augmenting the selective replication approach, that is, to replicate the most popular objects on multiple servers, with an in-network coherence directory that is implemented directly in the programmable top-of-rack switch. Our idea of using a coherence directory is inspired by CPU cache coherence protocols. It is a centralized directory that tracks which set of objects are currently replicated and the location of these objects. The directory processes all storage requests and forwards requests to the right server with spare processing capacity. And the directory ensures strong consistency among all the copies of the replicated objects. Let me illustrate Pegasus coherence directory with an example. Say three objects A, B, and D are currently replicated. We track both the ID and the locations of the objects in the coherence directory. One important benefit of the directory is that it can forward client requests to the right server without needing the clients to actually know it. When the directory receives a read request, it can pick the server in the object's replica set with spare processing capacity. Surprisingly, the other powerful capability of the coherence directory is that it can rebalance the replica set on every write. When receiving a write request, the coherence directory can select a different set of servers to forward the request to. The key point here is that to avoid subsequent requests reading the old version, we only need to update the coherence directory with the new replica set, because all requests will go through the directory first. There are, however, two major challenges. First, since the directory needs to process all traffic going to the system, how do we make sure it won't become the performance bottleneck? And second, how do we design a coherence protocol that guarantees linearizability, but without the expensive invalidation overhead in existing solutions? To address the first challenge, we observed that in a rack-scale system, all requests and replies need to traverse the top-of-rack switch. So the Tor switch essentially serves as a central point of the system, making it the ideal place to implement the coherence directory. Moreover, switches are designed to process packets at line rate, so they won't become the throughput bottleneck of the rack. Also, since the requests and replies need to traverse the Tor switch anyway, putting a directory there adds zero latency overhead. For the second challenge, note that since the switch processes all the requests, to guarantee strong consistency, we only need to have the switch tracks which servers have the latest copy of an object and forwards requests accordingly. And that can be done by updating coherence directory when the switch receives replies from the servers. But how to deal with asynchrony in the network, such as message drops, delay, and reordering? In Pegasus, we handle that with the lightweight version-based protocol. More concretely, we augment the coherence directory with two sets of version numbers, a single next version number and one completed version number for each replicated object. When the write request reaches the switch, the directory writes the next version number into the packet header and increments the number on the switch. Then the switch selects servers with spare capacity to forward the request to, in this case, S0 and S2. after the server processed the read request, they attach the same version number into their reply messages. When the reply message reaches the switch compares the version number in the packet header with the corresponding completed version number in the directory. In this case, the number is bigger, so the switch updates the number in the directory and resets the replica set to contain only S0. Now, when the second reply reaches the switch, the two numbers are equal, so the switch simply adds S2 into the replica set. Now, when a subsequent read request arrives at the switch looks up the replica set in the directory and can forward the read to either S0 or S2, both of which have the latest copy of the object. Our version-based coherence protocol has the following nice properties. It guarantees linearizability. All requests are completed in one round-trip time. The protocol is non-blocking, and importantly, it does not generate extra invalidation traffic. There are some other protocol details, including how to add and remove replicated objects, how to avoid duplicate requests, and how does the switch select servers for request forwarding. Or you can refer to our paper for more details. One point we want to emphasize is that selective replication in a Pegasus rack is for load balancing and not for fault tolerance. To tolerate server and rack failures, we use a multi-rack deployment and run chain replication across racks. So far, I have talked about the high-level design of the Pegasus coherence directory. We have implemented such a directory on a real barefoot Tofino programmable switch using a pipelined approach. In the first stage is a lookup table that checks if the key in the request or reply is for a replicated object. The second stage stores the directory version numbers and compares them with the version numbers in the packet headers. The third stage maintains and updates the current replica set for each replicated object. Once the switch picks the appropriate storage server for a request, the next stage rewrites the packet destination addresses accordingly. Lastly, we use the stage to track certain statistics, such as object access rate, for the controller to update the directory. One key benefit of the Pegasus design is that it enables very resource-efficient switch implementation. First, the switch only stores small metadata. Secondly, it only needs to maintain states for the small number of replicated objects. In fact, the system only needs to replicate the most popular n-log-n objects to achieve strong load balancing properties, where n is the number of servers, not objects. This result is an extension of a previous work on caching systems. Our switch implementation only consumes less than 3.5% of switch SRAM, making it feasible to coexist with other switch functionalities. Lastly, let me show you some evaluation of our system. In our experiments, we generate client requests following either a uniform or a Zipf key distribution, and measure the maximum throughput subject to a 99th percentile tail latency SLO. We compare Pegasus with two other systems. First, a traditional consistent hashing system with 16 virtual nodes per server. Second, netcache, a recent work that caches application data directly in programmable switches. Note that compared to Pegasus, netcache uses a lot more switch resources, and it has a number of restrictions on the workload, such as object sizes. First, we show that Pegasus is effective at load balancing and highly skewed read-only workloads. Here, we measure the maximum throughput of the three systems with increasing skewness in the workloads. Note that Zipf 1.2 is a very high skew level, but recent work has shown that such high skew does exist in real deployment. As you can see, throughput of consistent hashing drops significantly when the workload is skewed. Pegasus, on the other hand, is able to maintain its high throughput for all skewness levels. In fact, Pegasus achieves a 10x throughput improvement over consistent hashing when the workload is highly skewed. We can see that Netcache also achieves good load balancing. Actually, it has a higher throughput when the workload is more skewed, because the cache in the switch provides additional processing capacity. However, here the workloads are read-only. What happens when there are some writes in the workload? Well, here we use workloads with high skew and vary the write ratio. 0 here means the workload is read-only, and 1 means it's write-only. Even though Netcache performs really well when the workload is read-only, as soon as the workload contains a non-trivial amount of writes, its throughput drops by more than 80%. Pegasus, on the other hand, is able to maintain its throughput level across all read-write ratios. In fact, Pegasus achieves a more than 11 times throughput improvement over Netcache when the workload is read-intensive. In some other evaluations, we have also shown that Pegasus is equally effective at load balancing for various object sizes and for highly dynamic workloads. Please refer to our paper for more details. In conclusion, today I talk about our new approach to distributed storage load balancing by building a coherence directory directly in the top of rack switch. The directory tracks the location and forwards requests for the set of popular replicated objects, and simultaneously guarantees strong consistency. The resulting system, Pegasus, achieves a more than 10 times throughput improvement compared to existing approaches, and is equally effective under a wide range of workloads, including different read-write ratios and various object sizes. That is all for my presentation. Thank you, and I'm happy to take questions now.